let's take this statement and act on it with a del z bar and a del w. Okay, this I can do. So del z bar of t z z of z and del w bar of t z z w is equal to c by 2 del z bar del w bar of 1 over z minus w. You're tempted to set this to 0, but you must be careful because at z equals w is a singularity. So you must be careful. It's clearly 0 when z is not w. Z equals w, you have to be careful. So let's keep those things around. And we're worried about singularities at coincident points. Okay, now the next step is saying that from energy conservation, from diffeomorphism invariance of the regional theory, this thing is the same as del z of tz zz bar and z. And this thing is the same as del z z t z z bar w. Del w. Hello. No, not yet. I'll call you later. Okay. Fine. So, and then we take these del z and del w out. Okay. So what we get now is some statement about how the 2-point function, some derivatives of the 2-point function of zz bar and zz bar behave. Okay. Now we take the statement and integrate it once with respect to z and with respect to w. That integral will reduce this z minus w to the 4 to z minus w to the 2, and you pick up some factors. Okay? So what you have then is some statement which schematically, keeping track of no factors, is schematically tzz bar of z times tzz bar of w is like del z bar del w bar 1 over z minus w the whole thing squared. Okay, now 1 over z minus w the whole thing squared can be thought of as del z del w of log of z minus w. Again, keep track of no factors. Differentiating twice. Okay, so what this thing is del square in up to factors, del square with respect to z, and del square with respect to w of log of z minus w. Now you see why it would have been so dangerous to just say this was 0. Because del square of log of z minus w is not 0, it's a delta function. Anyway, we actually want to put a mod square here, but that's fine. That statement would remain true. Okay, so this thing is schematically like del omega squared of a delta function, which is precisely what we wanted to show. With some factors that you have to get right. So what I hope I've convinced you of, and what I would like you to carefully work out for this class, including all factors, okay, is that tzz bar z times tzz bar w in flat space cannot be thought of as, tzz bar can't be thought of as precisely the 0. It's something that has 0 expectation value. Okay, but its 2-point function has non-zero contact terms. These non-zero contact terms are completely determined by what we know about the theory, and in fact is given by this. Okay, which then implies that the 1-point function of the trace of the stress tensor in a background that is not flat but a little bit curved is non-zero. Okay? I'd like you to, okay, I'm not going to say more about this thing now. Go and think about it at home, and we come back and talk about it more next class. Okay. I have one more exercise I want you guys to try, which again, you go and think about it at home, and please.
This TU, so okay, this is just it's like an anomaly thing.
Yes, it's exactly.
Right. So this is a corresponding thing to how we calculate the anomaly. It's like
but I mean, yeah.
I mean, if you just proceeded in a standard QFT way and regulated and remove the regulator,
yeah,
we get this.
You would, in fact, Polyakov does this calculation in his book. Roughly that way. It's a little subtle though, for the following reason. That you must define T mu mu correctly. You see, you must define T mu mu as the response of the partition function to a change in conformity. Because if you thought of, if you wanted to ask what is, you might at first be possible, how can I possibly do this calculation in the standard way of doing things? Because I don't have an operator to insert. Suppose we're working with the free boson theory, for instance. The classical operator corresponding to T mu mu is 0. It's just 0 by equations proportion. Okay? Since not, as you say, it's an anomaly, and it's all in the measure in some sense. So, if you did it all correctly using standard quantity, then you will get it, but you have to do it carefully. Okay? This is a much easier way to do things, because it's very easy using usual techniques to get control of what T is doing. But then once you know everything about what T is doing, by diffeomorphism invariance, you know everything about what TZZ bars do. That's the basic point. Right? I know the 2-point functions of T, TZZ. Therefore, I know everything about the 2-point functions of TZZ.
So, okay. So, you have to know, like, since we use the energy conservation,
yes,
it's just some kind of a statement that if it was not so with the energy conservation.
Exactly. It's possible to set this this 2-point function to 0 exactly, but then you will violate the diffeomorphism conditions. It's the usual statement with anomalies. You regulate the theory in order to preserve some things, you must give up others. But you often have the choice about what to give up.
But energy conservation means expectation value of just the divergence of that operator.
Right.
So if energy conservation would not be violated if the
we don't want just that. We want the whole
word operators to hold.
Right.
Yeah. Word identities will be.
If you, basically, in order to derive this result, all we have used is the statement that we can replace this expectation value by this one inside the code. Okay? If that were not true, that statement were modified, you could modify that statement in a way to set this thing to 0. Okay? But this statement follows from some requirement. The requirement is essentially that diffeomorphism invariance of the theory be a good symmetry. Okay? And that we are going to treat as sacrosanct. It's the usual thing. It's like when you have a global and gate symmetry. You often run into a situation with anomalies where you are able to keep the global symmetry non-anomalous at the expense of making the gate symmetry anomalous. And you never take that option because the theory with gate symmetry anomalous is inconsistent. Same kind of thing here. The 2-point function of T trace with itself is 0, it's not 0, but okay, so what? But the theory was not diffeomorphically invariant, it would be very well, especially in string theory. Totally inconsistent. Okay? Fine. So, so go through this exercise, convince yourself of the logic being used here, and work out all the concepts. That's the first exercise. The second exercise, maybe I should just talk about the last exercise. Okay, maybe it's important. It's important now. I'll just talk about it in class. Okay, so just go through this, and then next time in class we'll finish up our general discussion of conformability theories, and then turn to a discussion specific. Okay, that's it. Okay, next time in class we will also find that we will, in a very related but similar, but in a slightly more conceptually interesting way, we will find the same result. We'll also talk about, how, you see, this was only step 1 of the exercise. We found the trace of the stress tensor. We'll also talk about how the whole partition function of the theory is completely determined from the statement in terms of the central charge. Yeah, I should talk about it. Okay, so that's it. Let's put the camera off. That's the discussion we want to have.